Hi everyone, today we are looking at the next gas law, Charles's Law. Okay, so we'll start off by looking at a few demonstrations here, just like before. Make sure you draw models. Again, it's really important that you're visualizing gas particles. And for each one, right, what's happening, and do your best to explain why, okay? So if you pay attention to the video, I explain why a little bit. But we're paying attention to two things today. We're looking at temperature, and we're looking at volume. Okay, so if you can use those words in your explanation, that would be awesome. So this is demo 1. We are looking at an Erlenmeyer flask with some water in it, and I've placed it on a hot plate. So what's going on is the water's boiling, it's producing hot steam here, and we're gonna see how this hot gas affects the volume of a balloon. Okay, so let's see what happens here. All right, this is gonna look a little funny, but we can see what happens to the volume of a balloon when we have a hotter gas. So what's going on inside is that the water is evaporating, so it's producing steam, gas particles, and those gas particles have a lot of energy, right? So they're bouncing around, colliding with the inside of the balloon. And so as they're bouncing around inside the balloon, right, they're pushing against the walls of the balloon, therefore increasing the volume of the balloon. Okay, so again, more collisions allow it to push the container, in this case the balloon, outward, and therefore the volume increases when we increase the temperature. All right, for demo 2, we're gonna see what happens when this balloon cools down. So just taking it off the hot plate, we can see that the balloon actually inverted. So think about what's going on here in terms of different gas particles, right? Which ones have more energy? Which ones are pushing harder right now? So we can see the balloon's actually inverted. I didn't even have to put it in the ice bath here. This is just from cooling it down. And so you can think about, where's there a greater pressure, on the outside or the inside? So the balloon is actually reverse inflated, and let's see what happens when I cool it down even more. All right, so the balloon is actually blown up the opposite direction once it has cooled down. Okay, so think about what happens when gas particles cool down. Well, how does that affect the volume, right? Are they colliding as often? Those are some things that can explain what's going on here. So you might want to think about what's pushing the balloon inward compared to inside of the flask here. All right, so Charles's law, as we just saw, demonstrates that volume of a gas is directly proportional to its temperature. So again, we're looking at those two variables. To do these problems, we have to use temperatures in Kelvin. So remember, Kelvin is equal to Celsius plus 273. I do want to mention this term right here, directly proportional. What does that mean? So what that means is if I double the temperature, the volume also doubles. If I half the temperature in Kelvin, then the volume also gets halved. So however you affect the temperature directly affects the volume. Okay, so make sure you know conceptually what's going on here. If I increase the temperature, what's happening to my gas particles? Well, they're moving faster, right? If they're moving faster, that's going to be more collisions. So we're really going to focus on these collisions when we want to conceptualize gases. How would that affect the volume? Well, that would increase the volume because the gases are colliding or pushing outward. All right, so more collisions allows gases to push outward more, therefore increasing the volume of a container that can change shapes, like the balloon we just saw. All right, so we're gonna solve some problems here. Charles's law problems, and we'll use this equation. So neon gas line is cooled from 100 Celsius to -25 Celsius. So right off the bat, I'm given two temperatures. So I start off with 100 Celsius and -25 Celsius. If the original volume of the gas was 2 liters, what is the new volume? So they give me the original volume, pardon me, and that is 2 liters, but I don't know the new volume. That's what we're solving for. Okay? So before we plug it in, let's convert these temperatures to Kelvin. So T1 is actually going to be 373 Kelvin. Remember, all you have to do is add 273. So let's not forget this equation either. -25 plus 273 gives me 248 Kelvin here. Okay? So now that I've got my new temperatures, my volumes are here, I can solve. So again, the equation is V1 equals V1 over T1 equals V2 over T2. Now all I have to do is plug in my numbers. So my first volume is 2 liters. My first temperature is 373 Kelvin. And I don't know V2, so I'm going to leave that as a variable. And then I'm solving for, and then my T2 is 248 Kelvin. To solve for V2, all we have to do here is to multiply both sides by 248 Kelvin. Okay, these get canceled out, and then we just do the math on this side. 248 times 2 divided by 373, and we get our final answer of about 1.33 liters. Okay? Try to include some decimals in your answers just to be more accurate. So when you're solving for volume, you just got to multiply both sides by the temperature beneath the unknown. Okay, so again, hopefully you're just going to review a little bit of algebra here and review this problem to help you with the practice problems. Let's do one more. This time, let's solve for temperature. So a sample of gas occupies 250 milliliters at 50 Celsius. So again, I always like to just write down all the information that's given and label it. They give me T1, 50 Celsius. The sample is heated and the volume doubles. So the volume is going to be 500 milliliters. What is the new temperature in Kelvin? So I don't know this new temperature. So again, just like before, we want to convert this temperature to Kelvin. So I'm going to add 273 here. And that gives me 323 Kelvin. Okay. Now that we have our numbers, we can go ahead and plug it in. So this is going to involve a little more math. Again, we're using this equation here. So I'm just going to go ahead and plug in the numbers. Well, we can write out the equation. So that'll give me 250 over T1 is 323 Kelvin equal to, we know the new volume, we don't know the new temperature. Now, to solve here, you're going to have to do a little bit of math and algebra. So we're going to multiply both sides by the reciprocal. So all of this is multiplied, and what that does we get T2 times 250 over 500. Okay, so now we just want to get the T2 by itself. Oops. Sorry about that. Now we want to get the T2 by itself, and to do that, we're going to multiply both sides by the thing on the bottom here. So we want to get rid of that denominator. 500 times 323. So that'll get rid of that on this side, and then we have 500 times 323. So this is milliliters. And this is milliliters times Kelvin. Lastly, we want to divide by 250 to get that by itself. Our milliliters will cancel out. And we get 646 Kelvin. Now, I know that was quite a bit of math, and I went through it quickly, but it is just algebra, and you should be decently well versed in algebra. And this is only when you're solving for temperature. So one way to avoid all that math is to just think, remember I said that volume and temperature are directly proportional? Well, if I had 323 Kelvin and the volume doubled, then I should also expect the temperature to double. So if I check my answer, 646 Kelvin is exactly double of what the temperature originally was. Okay, the key thing is that we need to keep the temperatures in Kelvin. So that's how you solve Charles's Law problems. Make sure you refer to this to help you with the 2 practice problems on your worksheet.